Hello everybody, and welcome back to another Eng 130 video tutorial. In this tutorial we'll be doing vector addition of 3 vectors using the CVN method. Alright, so looking at the example, it's actually the same example as the one that we did using the parallelogram method, except now we're going to solve it using the CVN method. And hopefully you guys find this method easier. I know I do, so let's begin. Alright, so I'm just going to kind of erase all this because this is for the parallelogram method, but we've already discussed we'll not be using that. So we're just going to start adding the 3 vectors. So the nice thing about the CVN method is it doesn't matter which vector you start with. You can start with any vector because in the end we still have to get into its x and y components. So I'm going to color code the vectors as I usually do so you guys can keep track of what I'm doing and where I'm at. So I'm going to start with F3. And the reason why I'm going to start with F3 is because it's actually the simplest. Since F3 runs right along the x-axis, there is no vertical component to it, as you guys can see. So we're only going to have to worry about one component, which is the x component, and change colors. And as luck would have it, so F3 x, the magnitude of it is actually just going to be 50 newtons. Because the only component F3 has is in the horizontal direction. So its only component would be the same as its magnitude. So we can write that F3 as a vector. Don't forget to put the little hat on. It's going to be equal to, and the little squiggly brackets, I'm going to put 50i, and it's plus 50 since we're going with the positive x-axis. And I'm just going to put plus 0j. And I like to put 0j just to kind of remind ourselves that we don't have any vertical components. And then don't forget at the end, you should always put your units. So it's in newtons. Alrighty. So as you guys can see, pretty easy. And the other vectors are just as easy, but they do have a little bit more calculations involved. So we're going to start with F2. And well, the reason why I'm going F2 rather than F1 is because F1 has a little trick to it, but don't worry, it's a good trick. It's not a bad trick. So F2 has 2 components, a vertical and a horizontal. So the vertical component kind of goes down like this. That's the vertical. And then it comes across horizontally like this. So we got F2, and I put Y for the vertical. And we got F2 x for the horizontal. So to find these components, there's 2 things you can do. Is one, I always, as you guys know from the last tutorial, like my angle with the x-axis. So I like to use that theta. Or you can do it with the 20 degrees. So either way works, but I'm going to use the theta, which is going to be 70 degrees in this case. So I'm going to put F2 x is equal to the magnitude. So we got 20 newtons times the cosine of 70 degrees. And once we type that in, we'll find that F2x is 6.84 and newtons. We can do the same thing for F2y. So F2y is going to be 20, except now it's going to be times the sine of 70. And when we type all of that in, we get 18.79 newtons. So finally, we have to write F2 as a vector. So as a vector, don't forget the little arrow at the top is equal to squiggle brackets. And then 6.84 I plus 18.79 J. So end the squiggle brackets, and then we put newtons. But here's the trick, and I hope that you guys picked up on this. This is incorrect. The math's all correct. It's 6.84. It is 18.79. However, and this is what you guys have to realize, and I'm going to put this in pink because the pink on here shows very well. Both of these vectors are going in the negative direction. F2x is going in the negative x direction, and F2y is going in the negative y direction. So this answer right here is actually incorrect because I have them both as positive. So you gotta erase that, and we have to correct them. So f2x is negative 6.84, and f2y is negative 18.79. So this is something that'll trick a lot of students, just because it's not really in the math, it's more your intuition. So it's not hard to see, but it's just something that you may forget. So please remember, you always have to check the directions, make sure that they line up. Alright, so let's move on to our last vector, and this one's my favorite because I tell the students about this and it's probably their favorite trick I ever show them. So, as I kind of mentioned in the, I think it was example 1.2, this exact example with the parallelogram method is a lot of people want to try and find this angle right here. Because what happens is with that angle, you make a nice triangle, so you can get F1y, and then you got F1x that goes around here, and F1x. So they want to try and find that theta in there to try and, you know, complete the triangle. And that works out well. It's completely fine. It's just an extra step, and I'm kind of lazy. I like to skip those tedious steps. That's why when they give you this little triangle here with the 3, 4, and 5, it's your best friend. And I'll show you why. It's because, let's say we want the x component of F1, and they give us the triangle. Well, we know it's going to be the magnitude, so that doesn't change. So it's going to be 30. Oops. It's going to be 30. But instead of having to go cosine or sine, all we do, and this is, actually I'll do this in a different color to show you because this is actually so nice. So if we want x, all we do is we take the x component and divide it by the hypotenuse. 30 times, oh, I keep clicking, sorry, 4 over 5. And, oh, I'm going to go back to blue. Back to blue. And what that does, if we type that into our calculator, what we'll find is this is 24 newtons. So that's why I love the triangle so much. You don't need to worry about cosine or sine or any angles. You just put its component divided by the hypotenuse. And the same thing is true for F1y. So its magnitude again is 30. But this time what we do is we take its vertical component, so this one's 3, and then we divide that by the 5. Oops. 3 over 5. And what happens when we do that is we get a magnitude of 18 newtons. So then we can finally say that F1 as a vector, so remember the little arrow at the top is equal to squiggly brackets, 24 newtons, so we go 24i, oops, 24i, and then we check the direction, so it's going in the left direction, so therefore it's a negative 24i, and then we check the vertical direction, it's going up, so it's positive, oops, plus 18j, and the squiggle bracket, and then we end with putting our units, so newtons. So we found all the components of all three of the vectors. We got F3, we got F2, and we got F1. So to add them up, it's literally how I just said it. We just add them up. So let's put F, the resultant vector, as purple. Let's say it's purple. So FR, so remember I put the R because it's the resultant. And then the X component is just going to be the X components of all the vectors added together. So going up, we got a 50. Plus, I'll underline it, so we got 50. We look down to this one, we got negative 6.84, so plus negative 6.84, and then plus, and then we look at the last one, minus 24. So we now know that here we go. We know that FRX is 19.16. And that's newtons. So then we can do the same for FRY. It's going to be all the y components added together. So the first one is 0, so we don't have to do anything. Looking at the second one, It's negative 18.79. So I'll just put in brackets. I gotta figure this out. Negative 18.79 plus, and then we look at our second one here, 18, so just plus 18. So we know that FRY is equal to negative 0.79 newtons. So easy as that. So there's two ways we can proceed now, as I was saying, is one, in order to find the actual magnitude, because remember, these are just the components. These aren't the magnitude of the vector. We can do two things. One is we can prove it out and draw the triangle using these, which I did in the last example to show you where all the formulas came from. But I'll give you guys kind of the secret is you don't need to do that. There's a formula for it, and as long as you guys know that formula, that's all we expect from you guys in exams. So from here we can go into the formula. So FR is going to be equal to, and I probably should have done this the last example, but because it's more of a 3D notation, but it should be the same for 2D. So when we're doing the magnitude of FR, when we're dealing with vectors, it should have two lines around it like this. That just means it's the magnitude. And again, moving forward in the course, this is something you guys will want to keep in mind, but yeah, so just keep this in mind. Whenever you see two lines around something, it means the magnitude. So that's the value of the vector that has no direction associated with whatsoever. So the magnitude of FR is going to be the square root of FRX squared plus FRY squared. So this formula is very easy to prove. I did it in the last example. It's basically you just draw a triangle using your two components. And then you can just use Pythagoras' theorem to find the c squared is equal to a squared plus b squared. However, in this example, if we solve it in, so it's equal to the square root of FRX squared, so 19.16 squared, plus, and 0.79 squared. So one thing that I do that I don't recommend you guys do, let me just make this a little cleaner. So one thing that I do, and I don't like that I do it, but it doesn't matter, is even though it's negative 0.79, I put it as positive because anything squared is just going to be a positive, so I'm just kind of being my lazy self by doing that. But in the end, you type that into your calculator, and you'll get that FR is equal to 19.2 newtons, the magnitude of FR. And that's the exact same answer that we got before. So everything is good to go so far. So 19.2. That's exactly what we're expecting. So now, the final thing that we have to do is just find, of course, its angle. So its angle is just as easy too. What we can do is two things. One, for the angle, I don't recommend it because there's the formula, but there's a reason why I recommend drawing the triangle for this one. So if we look at the components, we got FRX is 19.2. So I'm just going to go across because you guys all know I'm doing this. All right, so we got 19.2. And this will be kind of shown later why I'm doing this. Oh, sorry. 19.16, so that's FRX. FRY is negative 0.79. So it goes down. So 0.79. And then, of course, our resultant goes across like this, and this is FR. And, of course, we got the theta in between. So looking back at the formula, which I said works, so theta is going to be equal to the inverse tangent of, and then it's going to be the opposite over the adjacent, so the 0.79 over the 19.16. Oh, and I also do my brackets kind of at the top there, but I know that this has confused a lot of people, so I'll fix up my brackets. And then in the end, you type that all into your calculator, and you're going to get 2.36 degrees. So why did I draw out the triangle? Well, it's to show you that this 2.6 degrees is measured clockwise from the axis. You guys got to keep that in mind, because if you guys didn't draw this out, a lot of you guys may put that it was counterclockwise, like this, but that's actually incorrect. So it's best to draw it out, because then you can see which way the angle's going. So then finally, what you do is we have our magnitude, we have our direction. We can state that FR is equal to 19.2 newtons, and it's measured 2.36 degrees. But here's the trick, clockwise from the positive x-axis. And this is the same answer that we got before, so nice and easy. Oh, hold on, let me try and draw a box. So again, I'm always the fan of the box around because it shows this is the final answer. And that is a huge box, but this will work perfect. So that's the final answer. So just looking at our work, the steps are always the same for these type of problems for the Cartesian vector notation. 1, we want to find the components of all the vectors we're trying to add together. Second step, we add them together to find the components of the resultant force. And then finally, we can find both the magnitude and the direction of the resultant force using these formulas for 2 dimensions. For 3 dimensions, the formulas change a bit, but you'll see that later. For now, just worry about 2 dimensions. But the final thing I want to say is if you look at this work, it's much simpler and much smaller than that of the parallelogram method, which is why I love this method so much. So this is it for basically the material that you guys have covered this week, or the examples relating to the material that you guys have covered. But I thought that this isn't fair showing you guys these, because these are simple questions. These are the questions that professors show you in the lecture, and then you think, oh, this is easy. And then comes the lab and the final and the midterm, and of course the questions are nothing this easy. So what I'm going to do for the next couple examples this week is show you guys what I like to call some challenge problems. Some problems that you may look more like a lab. I'm not sure if they'd be as difficult as a midterm. Some will be, some won't be. But a lot of the ones I picked just contain little tricks to show you guys what to do. The nice thing about this week, though, is there wasn't really that many tricks. This week is just kind of more building your fundamentals for the following week. Because after this week, it gets a little more challenging, and then it becomes a lot more tricks. So, yes, I'll see you guys in the next example. Thanks, everybody.